Welcome back. In this video, we're going to investigate the first law of thermodynamics by applying it to a scenario involving a gas being taken through various states defined in terms of pressure and volume. I'm going to show you a method for tackling this problem and similar ones involving PV diagrams. So go ahead and take a look at the problem statement. Now in this problem, we're given a PV diagram telling us that a particular gas can be taken along various paths to get from A to B. It can either go from A to B directly, or it can go to this intermediate point C. And it gives us a little bit about the initial volumes and final volumes. The final volume is, for example, 3 times the initial volume. We also have a couple of pressures labeled in the graph, and it tells us, in addition, how much heat is taken up if you're going along path 1, and how much heat must be taken up if you're going along path 2 instead. The first question asks us to find the ratios of these two pressures. So I'm going to go ahead and solve that, and then we'll get to the next ones in a moment. These types of problems are just applications of the first law of thermodynamics. And if you have an ideal gas, which we're not getting to yet, there's a couple more things you can use. But when it's not an ideal gas, just any gas doesn't tell you it's ideal, then really all you have at your disposal is the first law of thermodynamics, which is that the internal energy of the gas can either increase by adding heat, or it can decrease if this does work. So if the gas does work, you're going to lose internal energy, that's the minus W. And if you add heat to the gas, if you heat it up, that's going to increase its internal energy. Now the way I solve these types of problems is by kind of organizing the heat, the work, and the internal energy in this graph. And what I do basically is, I guess it's more of a table, is for each path that I'm looking at, I write down, I can write down all the heat in this column, in this row, the work, and then I can just use this the first law to fill in any remaining rows. So if I know Q and W, I can just subtract them to get delta E. And it turns out sometimes you actually know delta E through other physical considerations, and you'll see that, well, I have Q and I have delta E, I can fill in W just by subtraction. So this is kind of a good way to organize your information, and a lot of times you'll find out that sometimes you have information you didn't know you had because it's so nicely organized in the table. So let's go ahead and fill in what we know here. The first thing we know is that the heat taken up along path 1, if you decided to go along path 1, is 5 P1 V1. So I can just fill that in here. And I'll write it in blue. And then secondly, we know that, well, let's go ahead and just fill in this column here. Let's just do, path 1 for now. And I'll have you guys do path 2. So for path 1, I know the heat is given explicitly in the problem. Now the work done is always the integral beneath the path. So if I'm looking at path 1, the integral is the area beneath this horizontal line. It's just the area of this rectangle here. And the area of the rectangle is the height, which is P1, times the width, which is 3V1 minus V1. So this is 2V1 times P1, which is 2P1 V1. And I can immediately find out the internal energy change along path 1. The internal energy change is the subtraction of these guys because of the first law. So the change in internal energy is just 3P1 V1. Let me have you guys do path 2. Do a similar thing I did here. There's some information given, some you have to find. Fill in the next column, and then we'll take it from there. For path 2, we have, it's given to us that the total amount of heat taken in is 5.5 P1 V1, so that one's straightforward. To find the amount of work that was done along path 2, just find the integral. And we can do it in 2 steps. Remember, path 2 includes both A to C and C to B. A to C is a vertical line which has no area beneath it. The volume doesn't change, so no work is done. There's no integral, so no work is done. So the work along A to C is 0. The work along C to B is the integral beneath that diagonal line, which is the entire area between that line and the x-axis, so that whole trapezoid. That includes, so that's the sum of the rectangle and the triangle. The rectangle area we found a moment ago is just 2P1 V1. And then the triangle is just the width times the height divided by 2, which gives you this quantity. Now, we need to find this ratio P2 over P1. So we could do the same thing we did a minute ago and just subtract these. Because of the first law of thermodynamics, the difference of these has to equal this quantity right here. But that won't really tell us anything because we just have a quantity with no equation to solve for anything. Instead, what we can do is use the fact that this path 2 and this path 1 had the same endpoints. And there's a particular quantity which is path independent. In other words, all it depends on is the endpoints, and that is the delta E. The internal energy, the internal energy change from this point to this point will be the same no matter if you went along this path, or some other weird path in any other direction. As long as you start at A and end at B, the internal energy change has to be whatever this quantity we found already is. So I can actually plug that in over here. So let me write that in green. So this is 3p1v1. And the reason we know that is because delta E is path independent. This is always very useful when they ask you to compare paths with the same endpoints. Delta E will be the same, so if you know it for one path, you know it for all paths. Now we can just use the first law of thermodynamics. This minus this must equal that, so just setting up that equation, we can solve for P2 over P1. So you should get 5.5 P1V1 minus that second quantity, 2 P1V1 plus, that must equal 3 P1V1 because delta E is path independent. And then canceling out the V1s and solving for this ratio, you'll find the following. You'll find that. Okay. So that's the answer to the first part of the problem. The second part of the problem asks us to find two things. First of all, which direction, if we want to make a cycle out of this. So now it tells us to ignore this going from A to B in either this direction or that direction. Now we want to make a cycle out of it. We can either go along 2 and then back along 1, or along 1 and then back along 2. The question says, which one of those should we choose such that this gas does work on its environment? In other words, the work it does is positive. So should I go clockwise or counterclockwise? And to do that, to see if the work is positive or negative, I would just do a quick geometric argument, which is just take a look at the integrals in the clockwise direction and then the integrals in the counterclockwise direction and compare their signs. In the clockwise direction, let's just start at A. We've got to get back to A by going along that path. So from A to C, the integral is 0. From C to B, the integral is whatever the trapezoid is. So the work done is whatever the area of this trapezoid is, positive, because I'm going in the positive x direction this way. Now when I go back from B to A along the opposite 1 path, this integral is going to be negative because I'm going in the negative x direction. So whatever this area is, I have to subtract it out. The leftover area is that triangle. Okay, but that's a positive quantity because this is bigger than that. Counterclockwise will give you the opposite thing. When you go along 1, you get a positive area this direction, but then when you go backwards along 2, you get this negative trapezoid area, or a negative trapezoid integral, I should say, which gives you a negative quantity here. So this is the one that does work. You want to go clockwise along the cycle if you want this gas to produce work. Now, the second part of that, kind of the sub-question says, now that we know that we were going to go in the clockwise direction, how much work will that cycle produce in one cycle? So if I go from A to C, back to B, and then back to A, how much work will this guy produce for the environment? Let me go ahead and have you guys solve that on your own real quick, and then I'll come back and say a few words about the physical process there, and then we'll finish up with the last part of the question. The work done by the entire cycle is the area of that triangle, which we saw earlier was just that quantity. If you plug in this ratio into that quantity to get rid of the P2, you'll find that the work done of the cycle is just 0.5 P1V1. Okay? Now, let me say a little bit about what's happening in the entire cycle in terms of the heat and the work done. So I'm going to actually use this, this table to kind of organize this information. And what I'm going to do for this last one is I'm just going to call this the whole cycle, so CW, meaning I'm going to go around clockwise from A to A. Basically, I'm going to go from A to C, C to B, and B to A. Now, you can see that obviously that path is just going positive along 2 and then minus along 1. So this is just equivalent to 2 minus 1. In other words, path 2 minus path 1. So if I want to find the quantities in this column, I can take all the quantities in this column and subtract the quantities in that column. And that'll give me, for example, the heat intake will be 5.5 P1 minus 5 P1V1, which is 0.5 P1V1. This will be a little more complicated, but the last one is pretty straightforward. The total energy change will just be 3 minus 3, which is 0. Now that has to be the case. Every time you have any sort of cycle in a PV diagram, whenever you come back to the original point you started at, the internal energy change has to be 0. You have to get back to where you started. So these numbers have to make sense in terms of canceling out to 0. And you see that now this is very useful because I can just fill in this guy by using the first law of thermodynamics. This minus this has to equal 0, so the work that the entire cycle does has to be 0.5 P1 V1, which we found a minute ago. So all these things are consistent. So this is really kind of two ways to look at this thing, and this is just kind of like filling in these missing quantities, but it helps you organize your information. Now physically what's happening is that this is what's happening the whole cycle from A to C to B back to A. The entire cycle takes in this amount of heat, and it uses that amount of taken in heat to produce this amount of work. And it has to be the same, otherwise it wouldn't get back to the original internal energy it had. All right, so you can think of like kind of a piston in a car where when the piston is compressed, you have the fuel coming in and then it's lit with a spark plug. And that heats it up very quickly, so it takes in a lot of heat. And that amount of heat is then converted to work, which pushes the piston back down. And that's how you get work by burning fuel. All right, and that happens every single cycle. So for that kind of case, you basically take in the amount of heat you take in is the amount of work you must produce. Now let's go ahead and finish up the problem. So the last part of the problem asks us to investigate what's happening on this vertical section between A and C in terms of work, heat, internal energy change, the pressure change, and the volume change. And I just want some qualitative answers here. So go ahead and jot a few things down and we'll come back and finish up the problem. On path AC, we see that the volume is held fixed at V1. So the volume is constant. And as a consequence of that, because it's a vertical line, there's no integral beneath it, no work is being done. Yet at the same time, we see that the pressure has increased from P1 to P2. Equals 0. Pressure has increased from P1 to P2. How does the pressure magically increase if we're not doing any work on this gas? Well, think of a pressure cooker. In a pressure cooker, when you have it on a stove, the volume is constant. Once you put the lid on, the volume doesn't change. You hold the lid tight, and then how does the pressure inside of it increase? Well, you turn the gas on. So you have to somehow put heat inside of it. So we know that here, in this case, based on that analogy, the heat somehow must be going into the gas. Okay? Now, using the first law of thermodynamics, if this is positive and this is 0, we know that the internal energy change must be positive. So somehow the internal energy of this gas must be increasing. And we'll see when we get to ideal gases that this internal energy change is going to be proportional for ideal gases to a temperature change. In other words, going back to our pressure cooker analogy, as you start to heat up the pressure cooker from below, not only is the pressure rising, but the temperature will be rising at the same rate. And so we'll see that for ideal gases, this will immediately tell us that we can find out the change in temperature as well. Let me go ahead and stop there. We've done a few different parts of this problem, so I want you to go back, take a look at how we solve this, take a look at this table method, and try to use this method for future problems involving PV diagrams in which you may have some quantities but are not sure what you're missing. And you'll find out a lot of times that as you start to fill in some quantities of this table, other things will just start to magically fall out. So go ahead and take a look at the summary, and we'll see you next time.